All right. Well, while PowerPoint is thinking about our next slide, um, what branch cache enables you to do is make data that's far away look like it's closer. It's a tool that we use between the client, the server, and other devices on the network to reduce customers' bandwidth costs and reduce user-perceived latency. And it's a platform that applications can build on top of so they can avoid reinventing peer-to-peer sync every time you build a new application that needs it. So we're going to talk about how branch cache works and some of the improvements that we've made in Windows 8. Before I dive into this, just to give me an idea, how many of you are intimately familiar with branch cache already? Okay. And some general understanding or never heard of it? Okay. Then we're going to start off with just how branch cache works, going a little bit deeper than sometimes when I present this. We'll talk about the changes that came in Windows 8, and we'll talk about moving it beyond its traditional role, which has been from a branch office to a central office, to talking about any location onto a data center. So to begin with, all right, this PowerPoint is going to be this slow. All right. Now, a lot of internet protocols were designed for this situation. Your server and your client are close and the connection is fast. I remember when I was in college, I had a file server, which was the only other thing on a 100 megabit switch from my desktop. I loved that situation. Really high bandwidth, very responsive. I wish that were the world in general. The reality is, though, that's not what most users have. Servers have moved into the cloud. Servers are being centralized in one office while users are distributed across many branch offices. And bandwidth, while it is becoming cheaper, there was a nice article in the Seattle Times this morning about a new fiber internet provider in the area. Although it's becoming cheaper, bandwidth is still a limiting factor in a lot of cases. Enterprises don't want to pay to deploy higher bandwidth links. And at the same time, that causes things to get very slow. No one really likes waiting to access their data. So the way we solve this in branch cache is to take the devices that are accessing the data and let them work together to reuse the data that they've downloaded and reduce the amount of bandwidth that we need going back to the central server. Branch cache works in two different modes. The first of these is distributed cache. So let's walk through a sample interaction with the server on the distributed cache. You've got a branch office with two people that we're going to be looking at, and they are both going to access the same document. Now, Alice gets there first thing in the morning, bright and early. Nobody else is in the office yet. She goes to access the file. So she clicks a link or whatever to access it, and her PC goes to the central server. And instead of downloading the content itself, it downloads a set of identifiers that describe the content. And then her PC is going to broadcast on the local network, looking for anyone else who has the data that matches these identifiers. Now, since she is there first thing in the morning, nobody else does. So she has to go back to the server, and her PC is going to make a second request and download the actual data. So what did branch cache achieve for Alice, who is there first thing in the office? An extra RTT. Sorry. Where branch cache actually shows a benefit is when you get the subsequent request. So you have Bob, strolls in around 10. He goes to access the same thing. His computer sends a GET, pulls down the identifiers. His computer does the broadcast and finds that Alice's computer already has the data that corresponds to those identifiers. So instead of going back to the server over a link that is probably fairly slow, fairly high latency, it's going to pull over the local network the copy of the data that's on Alice's computer. So you can retrieve that local network bandwidth, local network latency. So for him, that download looks much, much faster. Now, of course, there's a obvious difficulty with this model, and that is that Alice is not in the office 24/7. So she got there early. Shortly after Bob got into the office, she walks out for lunch. And since that cached copy is on her computer, when she walks out for lunch, if it's a laptop, the cache walks out for lunch. So if somebody were to try to access it during lunch, now, by this point, Bob has a copy, but if somebody were to try and access it when there wasn't someone else who had a copy, you would have to download it from the central office again because you have parts of the cache that are walking in and out of the office or going to sleep in the case of a laptop that's got its lid closed. So to address that, we have the second mode, if PowerPoint will accommodate us, where we have an intermediary. And that intermediary is the hosted cache server. So the story looks pretty similar. You make a GET to the content server. You download the identifiers. But instead of broadcasting, you make a unicast query to the hosted cache server to see if that data is already stored. It's not. So you make a second GET to the server. You pull down the data. Same flow as in the distributed model. You're just using a unicast instead of broadcast. But then, after you've downloaded the data, you go back to the hosted cache server and inform it of what you've just downloaded. So the PC will send over the identifiers and say, I now have the corresponding file if you want it. And the hosted cache server can pull it from Alice's computer. And then that copy is stored on the server locally, even if Alice puts her computer to sleep, goes out to lunch, whatever. So that when Bob goes to access it, he downloads the identifiers, searches on the cache server, and finds the data. Now, this is a self-populating cache, effectively, because the hosted cache server doesn't need to be configured as to what it's going to cache. It's going to contain whatever people in that office have recently accessed and have offered to the server. So things that are accessed frequently stay in the server's memory. Things that are not accessed for a while eventually get evicted. So if you think about the two different modes, you have distributed, which is definitely the advantage that you don't need a whole lot of infrastructure there. It's PC to PC. If you have a branch that doesn't have a server, doesn't have some appliance for acceleration, you just turn this on over group policy, and the PCs work together to accomplish this. Now, the downsides of that are that it's broadcast, so it's limited to a single subnet. If you have wired and wireless clients that are on separate subnets, they effectively form two different caches if you're using distributed mode. You get around both of those by using the hosted cache, where you have unicast, so you don't need the broadcast. You can cross different network segments. The availability is high because presumably your server is not going anywhere. And you can use an existing server. This is not a heavyweight service that needs to run on the server and requires its own dedicated box. It's also helpful in large branches because the server can scale to many more machines than you can put on a single subnet and that you really want generating all that broadcast traffic. So where we don't recommend distributed mode for more than about 50 clients, you can take server to hundreds. I think we have a couple instances running with thousands of clients on a single site. Branch cache is exposed most availably to apps through a set of APIs that run on Windows that lets you break it down into a couple different roles. You have the server side, where you're going to feed content in and get out the set of identifiers. You have the content information structure, which contains the identifiers and have everything that the client needs to be able to perform the search locally. That's what gets passed across the accelerated protocol to the client, and the client then feeds them into the APIs to do the search locally, see if the content is available from someone on the network, from your own local cache, or from a hosted cache server. And the advantage of doing it this way is that we don't really care what the higher level protocol is. From the branch cache level, it can be a higher level protocol we've never heard of. It can be your custom protocol. It can be something that's built into Windows like HTTP. All that matters is that there's a way to get this content information structure from the server to the client, and that the client and server both support branch cache to generate that. So to look at the architecture within Windows, we have the platform at the bottom. We've got HTTP and the SMB stacks within Windows already have this capability built in on the Enterprise Edition. So the platform itself is available on Pro and higher. The protocol integration for HTTP and SMB are available on Enterprise and higher. But anything can build on top of the APIs directly. So for example, in Office 2013, they took their Cobalt protocol that they use between Office and SharePoint and hooked that into branch cache so that even running on Pro, if you have a SharePoint server with branch cache turned on, you can then use that among machines that have been accessing the same file from a SharePoint server that is remote. Now, since this is an Interop Plugfest, I wanted to highlight what the different protocols are, and I apologize for the alphabet soup of the protocols here. I'm sure if you're used to dealing with Microsoft protocol documentation, you've seen these before. So we have PCC is the prefix for all of these. This is the Pure Content Caching, PCCR, Pure Content Caching and Retrieval System. So you have PCCRD for discovery. That is the broadcast, does anyone have this data protocol. That tells you where you're going to get it if you're in distributed mode. If you're in hosted cache mode, you already know where you're going to ask if the content's available. Either way, you use PCCRR, which is the retrieval protocol, to pull it from the pure that you've identified or from the hosted cache server. And then if you're using a hosted cache, you need to inform it of data that you've downloaded that it doesn't have, and that's PCHC. The other two that are highlighted here are our extensions to HTTP that lets you pass the ability for branch cache to the server and pull down hashes as an extension. So we do that as a different accept encoding. So the client would advertise that it accepts content over HTTP that has been encoded as gzip or encoded as PureDist, pure distribution. And if the server also supports that, then it will send back that the content encoding that it's using is PureDist, and what follows is the content identification structure. SMB, as of version 2.1, adds file operations that retrieve the content identification for a given file that you're trying to access. So one obvious question here is what the security model would be, because you probably don't want to be able to go ask your neighbor's computer for any of the files that they've accessed. You can imagine if I wanted to go ask my manager's laptop for all the reviews on our team. That might not go over so well if that worked under branch cache. We encrypt the data in transit between clients so that you can't overhear what's going on. Also, because the data is encrypted, even if you ask somebody for a given piece of file, unless you have the key, you can't decrypt it. So we help to prevent unauthorized attacks. And the other piece there, looking at security from the other side, a lot of WAN optimization strategies have trouble with encrypted protocols. So if you're using IPsec or you have TLS, if you look at some of the other WAN optimization devices out there, what they'll wind up doing is putting these certificates on the WAN optimizer, terminate the SSL connection so they can see what's being passed, do their optimization, and on the other side, they may open a new SSL encryption, a new SSL connection, or just pass it unencrypted. Because we're riding inside the accelerated protocol, all we care is that the content identification gets from the server to the client. The channel in the middle is completely opaque. We don't know what's going on. It can be encrypted, and that's fine. So to think about how we prevent guessing attacks, we've got a series of identifiers and hashes that the server will build, and only some of that gets passed to the client. So we start with the different blocks that the data is chopped up into. And each block gets hashed. We take a hash that represents the entire segment. We take that segment hash of data along with a secret key that the server has, and we come up with a segment secret. So this is coupled to the segment. It is based on the server's key, which means that even if you have the same data from two different servers, you'll have different segment secrets that go along with that identical data. And that helps to deal with guessing attacks. So going back to, I want to get the team reviews off of my manager's computer. If we didn't have this, if there were no server secret, what would happen is I would generate my own file that said, I got the highest review possible. Generate hashes, broadcast, does anyone have that? Well, no, darn. Well, scale it back a notch. I guess that instead of a 1, I got a 2. Broadcast it, yeah. This way you can't do that because there is the server secret that you have to know in order to generate the same segment identifier. So we have the ID that is based off of the segment secret and the hash of data. And then we actually pass that segment secret to the client. And so what happens is that when the client goes to make the initial request, the server does all the authentication and authorization that it would normally do in order to figure out if the client has access to that data. The client doesn't get to request anything that, from peers without talking to the server first. When the server passes back the content information structure, that contains the segment identifier and the segment secret. The ID is public. You can send that to anyone. The secret is what you use to decrypt it once you get the data back. So you do your broadcast in distributed mode, and you send out the segment ID. You find a peer that has it. You retrieve it. And what you have in flight there is encrypted. So it doesn't matter if, if anyone overhears it. We can transfer it over an unsecure channel. And then we decrypt it locally with the segment secret. Yeah, so the segment secret is generated on the server. Oh. So the question is on how the client would calculate the ID and the secret. If we can.
Yeah, I know. So there's the segment secret, which is a combination. It's a HMAC under Peertist one. It's an HMAC. Mm-hmm. So it takes the segment ID and the encryption key, which is an MD5 or actually SHA-256, sorry, and uses a HMAC SHA-256 to calculate the segment secret. Mm-hmm. Right? Okay. So that's on the server side. Mm-hmm. Right? Okay, then
I'm going to trust you on what the hashing algorithms are because I
under Peertist version 1. I don't know Peertist version 2 yet, but yeah. Okay. So go ahead to the next page then. All right, the server
The server sends the content identification structure to the client.
Right. The whole content information.
Mm-hmm.
Right. Okay.
And that, I'd have to pull up the protocol docs to see, to remind myself how it's formatted, but that has both the key that the client needs to decrypt it and the identifier that it shares.
No. Not to my knowledge. Under Peerless version 1, the client never sees the key, because if the client saw the key, then the client could generate false information.
If the client saw the server secret,
Right.
but we're not talking about the server secret here, we're talking about the segment secret.
But what the slide says is that the client calculates the segment secret.
The
Next slide.
Okay, so the calculation would be the encryption KE equals KP here.
That's the
So
key. The encryption is the KP equal hash HOD comma KS.
Right.
That's
so,
the encryption. That's the signing essentially, but it doesn't matter. It doesn't work as a signing. It's really more of a fingerprint because you can't verify the signature.
Right. So it may not be perfectly accurate to say the client calculates it, but I think the client does. The client does get the segment key. The client does not get the server key.
Right. It gets the segment secret, which is not a key. It's a fingerprint.
Well, yeah. The secret that is, which is used in exchanging the encrypted version with peers.
That okay with peers?
Yes.
Because that's a separate operation.
Right.
But the key from the server is never brought in.
Right. The server secret, and I know they're similarly named. The server secret is never shared with the clients.
Right.
The segment secret
is in the clear.
Right.
It's plain text.
Well, it's over the accelerated protocol. So if you're doing plain text HTTP,
right,
then it's in the
see
clear.
it. Right.
Yeah. So that is highlights a good point that branch cache is never more secure than the accelerated protocol. So.
Or the unaccelerated
right.
protocol.
The protocol that you're running branch cache over. If you're running HTTP without TLS and you're passing things in the clear, then the server just downloaded that key in the clear. So even though things are exchanged with peers encrypted, the key was passed in the clear. So if you were sniffing...
I'd call it a secret, not a key, because it isn't used for locking anything.
Okay. If the secret was passed unencrypted, there's no effective encryption in the exchange. But if the channel with the server is encrypted, then the secret that was passed doesn't ever go in the clear because the clients don't share that secret among each other. They share the ID. So yeah, too many similar terms, I acknowledge. I think we've had some TDIs on confusion between what the terms are there. So
I've probably sent some of them in.
I appreciate helping make the docs better. I've occasionally inherited some that were not in the greatest of shape. So looking at the things that have changed in Windows 8. Excuse me. A lot of our improvements, we have moved the protocol version from 1 to 2. So there are breaking changes in the protocols. And a lot of that is around chunking improvements to let us get better bandwidth savings. We also have some implementation changes around deployment and management and around scalability. I'm not going to go into those as much because this is more of a protocol-focused talk. But I want to mention that they're there. Server 2012 is better than 2008 R2. So one of the first areas where we make improvements is performance. In Windows 7, and specifically in PureDist version 1, segments were, if I remember the sizes correctly, 32 megabytes with blocks of 64K each, where the last segment was allowed to be smaller than 32 megs because you can't expect every file to be an even multiple. And the last block was allowed to be smaller for the same reason. The improvements that we've made in branch cache get better chunking by allowing variable size segments. So we've somewhat collapsed the distinction between segment and block. And in version 2, segments are always one block long. They are variable sized so that you have anywhere from 32K to 128K length blocks. The way we generate that is instead of doing a fixed size, we take the content, we run a fingerprint algorithm over it. Question?
So this chunking is part of branch cache version 2, is that correct?
The improvement is part of version 2,
Okay.
yes.
And we still haven't gotten to the point where we're talking about Windows Server 2012 R2 specific changes.
2012 R2 does not have a protocol level change.
Okay.
So in 2012 R2, we have implementation changes that, for the most part, are targeted at improving the performance on hosted cache server, but the protocols will be interoperable with version 2 as well. We wanted to avoid introducing more breaking changes to the protocol because right now you already have Windows 8 being able to fall back to version 1 when it's dealing with a server 2008 R2 content server or hosted cache. But then you lose a lot of, you lose particularly the chunking improvements here because those are specific to version 2 and allowing the variable size blocks. So this is going to be true in 2012 as well as 2012 R2. So using the fingerprint function, and we can run it across the data, find the maxima or the minima. This is not actually using the RDC algorithm, but it's very similar to what remote differential compression uses. And in fact, because it's implementation specific, if you are writing the content server, you can come up with your own chunking algorithm. Doesn't matter exactly what it is, so long as the blocks are valid sizes. And conversely, if you're not writing the server side, you don't need to know what the chunking algorithm that the server used was. In Server 2012, this is actually the same algorithm that file server deduplication uses to break things up into chunks. So then, using the fingerprint, we come up with our variable size blocks, and then we take our block hashes for each of those. So the advantage here is what happens when a file changes. Version 1 of branch cache was very good for files that were largely static. You had large chunks that could be retrieved from peers as a block at a time, build up a segment, reuse the segments, and reconstruct the file. Now, the difficulty with that is that if you have a change that is exactly the same size, okay, you invalidate a segment, you have to re-download the new copy of that segment, and you can reuse the others. But what if you have a change that replaces adds a new byte at the beginning of the file? If you have fixed size segments, you've just invalidated every segment. So the improvement here is that by having a fingerprint function, we are likely to come up with the same splits later in the file. And so even if you insert a byte at the beginning, you only invalidate that first segment. And with the segments being smaller, that's much less that you have to fetch from a peer. So on files that change frequently, this increases your odds of finding a hit from peers or from the hosted cache server. The other improvement that we have is specifically on the HTTP requests. So one of the things that you would run into, particularly when you're trying to set up a demo of branch cache, is that the first request, at least to a Windows server, doesn't actually get hashes. The first request tells the server that there are branch cache capable clients out there and tells it to start generating the hashes. And so it would be the second client that would get hashes back, discover it doesn't have the content. The third client would then actually find the content from up here. And that only has to happen once on each set of content, but it can delay you when you get started. So what we now have is an extra option in our HTTP extensions where the server can say, I don't have hashes for you, but I am generating them. And then the client can queue a task to go back 30 seconds later, fetch the hashes for the data it already has, and add them to its local cache. So that just helps us skip past that problem of needing to generate hashes, and the client will never get them and not be able to share even though it has the data. And just to point out that that limitation was not really a protocol limitation in version 1, but an implementation where we didn't attempt to generate the hashes in advance. We had a tool that you could run. The other improvements that we've made are particularly around deployment and management. So we have some deployment improvements that come from being able to use Active Directory to locate the hosted cache server. So previously, what you had to do was configure each site with a GPO that told it what the local hosted cache server's name was. Because when Windows clients were going to look for that, receive that group policy, know the name of their hosted cache server, and talk only to it. The improvement we've made with the Windows 8 clients is the ability for a Server 2012 to register itself in Active Directory with a service connection point so that clients can go out and receive the root policy that tells them to turn on branch cache and to do hosted cache discovery. Then they'll look for a service connection point for their site. If they find a hosted cache server, they use it. Otherwise, they fall into distributed mode. The other improvement that we've made is because the hosted cache server receives the encrypted content, it doesn't actually have a need to decrypt the content. It doesn't need to know what content it's received. So on the implementation side, we're storing the blocks encrypted as they come in, never decrypting them on the hosted cache server. So that means we no longer require or strongly recommend the presence of BitLocker on the hosted cache server. That also means that since the hosted cache server isn't receiving the segment secret, then it doesn't need to, the conversation with the hosted cache server doesn't need to be over HTTPS. So we've moved in version 2 to using HTTP instead. And by having the cache server auto-discovery, we reduce the need to have a site-specific GPO when you have Windows 8 clients. Unfortunately, that is not something we were able to take down level to Windows 7. So configuring Windows 7 clients to use a hosted cache server is still a per-site GPO. And I mentioned with the reduced need for having the BitLocker and the certificate on the hosted cache server. In version 2, we don't transfer the segment secret to the hosted cache. Therefore, we don't need the certificate. And we actually got a performance improvement out of this because we're not doing unnecessary decryptions and re-encryptions. You look like you have a question.
Just I probably missed something. But you're not transmitting the segment secret, okay?
You're not transmitting it between peers in distributed mode.
Okay.
In PCHC version 1, the hosted cache server got the segment secret when it technically doesn't have a need to.
But I thought the reason for it was to verify to the client that because there's no way to check it as far as checking the signature. But it was a uniquely generated value that could only be generated correctly by the server. Mm-hmm. So when you got it from the server, you could use it to match what you were getting from the hosted cache or from your peer. Mm-hmm.
But if I'm understanding correctly, version 1 distributed mode didn't share the segment secret, right?
Distributed mode never shares the segment secret
In either version 1 or 2.
Correct.
Right. So if version 1 distributed mode didn't need it, then hosted cache mode also technically didn't need it for any functionality.
Right.
Then why was it there?
Design choice.
But
And
that's
a
not, but, okay, that's why I'm confused, because it was explained when I first heard of this protocol. It was explained that you've gotten this piece of information, this fingerprint, and now you can verify that that is what the same fingerprint that's being found on your cache, wherever the cache is located, because you have this value that could only have been generated correctly by the server.
Right. So the client will have gotten that value from the server, and then we'll have asked the hosted cache for the encrypted content that the hosted cache server already has. So the client is still doing that validation. There is just no need to send that secret to the hosted cache server.
On the request.
At any time, actually.
Well, the hosted cache doesn't need to store it, because the client will always go to the main server first and get the segment secret from the server.
But then you're never verifying it against the cache information.
You get the cache information from the hosted cache and you verify it upon receipt.
How?
For the segment secret you got from the server.
So I think the point that you're going to is the hosted cache server can't verify it.
No, it's the client. The client has these various tags, right? One of which it can only be generated from all the others, and a secret that you don't know, right? When it gets this information, it goes to the hosted cache, says, I want their actual content, all right? If it doesn't present this secret to the hosted cache, and if the hosted cache doesn't have a copy, there's no way to verify it. So it's a completely useless field then.
The client presents the segment identifier,
right?
Which is not the secret. It can, just like it could broadcast it, it could send it to the hosted cache server and get the content back.
It doesn't matter where in the cache it's getting it, peer-to-peer or hosted cache. At this point, we don't care.
Right.
Okay.
So just like you don't need to send it to a peer, you don't need to send it to the hosted cache server.
Then what is it used for?
To decrypt what you receive from the hosted cache server. Because the hosted cache has no proof that you're authorized to access the data. It's just going to give you the encrypted blob that's associated with that segment ID. Then when the client gets it, it then has to decrypt it using the segment secret.
Got it. All right. Got it.
Exactly.
Right. Okay. Got it.
So if you know the segment ID of something you're interested in, you can freely fetch it from a hosted cache server, from a peer, or whatever. If you know it exists, you can retrieve it. But without, in order to get the secret to decrypt it, you have to go back to the origin server, which is going to check that you're allowed to access that data. So from a cryptographic sense, the security of the secret is the security of the data. In version 1, we shared the secret with the hosted cache server. There was no technical reason why it needed to have access to the data, so in version 2 it does not. All it gets is encrypted blobs that it doesn't know what it maps to. So this turns out to be a performance improvement because previously we were getting the segment secret, decrypting it, and storing it decrypted on disk. And then when a client came and requested it, we would have the segment secret that we still had stored, re-encrypt it, and send it to the client. Now we just keep it encrypted the whole time. Although that is implementation specific to Windows. For discovery, we use service connection points to discover and connect to hosted cache servers. So a hosted cache server that is configured for a particular site can register an Active Directory that it is a hosted cache server for that site, and clients can just query an Active Directory to identify anything that's local and see if they want to use it. I'm going to click out of here. And I'm going to do the exceptionally risky thing of doing a demo on live machines. And let's start with the client. So what we have to begin with is a site that is stored on a content server. These are all VMs on the same server, so it's going to be a little bit slow. I was saying earlier, this isn't really a server class machine that is running 5 different VMs. But one of those is using a tool that artificially slows down its network connection to make it look like it's remote. So when this client goes to access that site, you're going to see that it takes a little while to load up. So this is a link that looks like it has a 1 megabit per second bandwidth on it and about 40 milliseconds of latency in each direction. So you notice that loaded fairly slowly. Internet Explorer is set to clear cache when I close it, so we're not going to get a repeat of that site if I load it again. So we're going to go now on the domain controller and configure branch cache. And I normally turn up the DPI a little bit, and Remote Desktop doesn't accommodate me as well on that, so everything is really tiny text on this display. So the group policies we're going to deploy on the domain here. We're going to first turn on branch cache. That just enables the service, and if that's all you did, then branch cache would be running in local only mode, where it doesn't ever broadcast or ask a hosted cache server. It just looks at the chunks that it has stored locally. We can enable distributed cache mode and enable hosted cache discovery. So with that combination of policies, what every client is going to do is check an Active Directory, see if there's a hosted cache server that's local to its site. If there is, it'll use it. If not, it'll go to distributed mode. And then the other thing that we need to do here never remember where the firewall rules are. So we also need to push down some firewall rules to the clients so that they will allow the traffic to come in and out. And we've got predefined rules for content retrieval. And we'll also put in a predefined rule for content discovery. And with that group policy, branch cache is turned on for all the clients in the domain after they do a GP update, obviously. So the other thing that is new as of Windows 8 and Server 2012 is PowerShell support for branch cache. So you can do get BC status to see what the current setup is on this machine. And since it probably hasn't refreshed its group policy, it's going to say every branch cache is enabled is false. So I can do a GP update, pull down the new group policy, and if we repeat BC status, we'll see that it is now in distributed mode. Now to configure a hosted cache server, also using PowerShell, I just need to do enable BC hosted server and tell it to register itself with a service connection point in Active Directory. And wait while it turns on that role. And now if I get BC status here, we'll see that branch cache is enabled. This one is running in local mode because it is the hosted cache server. And hosted cache server is enabled is true. So now if we come back over to a client, without changing the group policy, I need to be an administrator for that. So if we stop and restart the service, it'll do hosted cache discovery and discover that it is now a hosted cache client, where before it was a distributed node. So no need to change the group policies. When a hosted cache server comes online in Active Directory, now the clients just find it and start working with it. So what we're going to find is that accessing the intranet site, again, is a little bit slow because you don't have anyone else that has downloaded this content that you could pull it from. I could click on a link here just to get an idea of what the general speed of this site is. Got a PowerPoint that I'm going to save, and between the time I spent talking about it and the time it took to actually download, that was about 10 seconds to download it. We can click on the training video. And media player comes up, it's connecting, takes a little while to buffer, and then starts playing. So now, if the demo spirits are with us, going over to client 2, and actually, before we do that, we need to do GP update over here so that it knows branch cache is turned on. Come on. So now we get BC status. Interesting. I'm not sure offhand why the PowerShell commandlet was failing, but let's see if things are any faster here. All right, let's, if you will forgive me for a moment while I quickly see if branch cache is running here. And if not, then we will pass on the demo, and my apologies. Branch cache. Okay. I do not know why the branch cache service is not starting, so I will pass on this for right now. Although one thing we could probably do we'll just clear out the cache so that we know nothing is left in IE here, and we can reload it here from this machine. And you see things pop up with a good bit more response time. It still has the latency because it has to go to the server and get the content information structure. So the best example would be where there's no latency but constrained bandwidth. I can download this again, and notice that was very fast. If you did that in IE, it still fetches a new copy of the file, but over branch cache, it finds that the file hasn't changed. And if we open the training video,
safe and secure to.
We don't really care about watching the video. One moment while I catch back up to where we are. So the other thing that has changed with the Windows 8 clients is the ability to deal with multiple hosted caches in parallel. So along with the automatic discovery of what hosted cache servers are available for your site, you now no longer need to deal with just one hosted cache server. You can query from several as to what data is available, and then download from whatever hosted cache server has the data that you're looking for. So we already had logic to let us retrieve from multiple peers. That's distributed mode. So taking similar logic and applying it to the hosted cache server just makes sense. Uploads are still only done once. If we download content that no hosted cache server had, we pick one at random and upload the content to that hosted cache server. And this lets you have better scaling and availability without needing to set up the complexity of a cluster. So you just have multiple cache servers per site. If one of them goes down, oh well, the client will use the others. So thinking about how branch cache could be used in a cloud infrastructure, even though it was originally targeted for dealing with small remote offices, if you think about it, the difference between a remote office and a central office is not that much as compared to any office and a data center. You still have latency, you still have bandwidth constraints, and it is probably faster to talk to the guy next to you than to talk to the data center in Tukwila or San Francisco or wherever it happens to be located. So conceptually, accelerating a protocol dealing with the cloud is no different than something that's going internally to something that's in the central office. And you can do some of branch cache even without server-side understanding by letting the clients play the server role as well. So thinking about different places where branch cache would come into play dealing with the cloud. If you have a virtual machine or cloud endpoint, If the protocol already has branch cache acceleration, just keep using it. There's no need to change there. You can use it when you're transferring data between two data centers, if you have data that needs to be replicated. And if you're dealing with public cloud infrastructure that doesn't support branch cache on the server side, all the same problems still exist. Even if it's not generating hashes, your data is still far away, and there are advantages that you could get by using branch cache to hit it locally. So the way that you can do that is generate hashes on the client. This requires the clients to have some trust, because now the clients know the server secret key. So you, again, have to lock the server secret down with something else that is at your layer. So to give an example of how you might do that using Azure Storage. So Azure does not generate branch cache hashes for clients. So if you have a client that wants to put branch cache capable data in the cloud, they can use the APIs on Windows or your parallel implementation of a similar chunking scheme. Run it through the APIs and generate both the data and the content identification. Then you upload both of those things to the cloud as separate files. And then the client that wants to access it knows the relationship between the two by your higher layer protocol, downloads the identifiers, uses, in the Windows case, the local API to do exactly the same search with the peers or the hosted cache, and fetch it from the data if it needs to, and feed it into the local cache. So that means that there is a little bit more that needs to be done by the application that's calling branch cache, because you're effectively playing both the client and the server roles. But it means that you can take advantage of branch cache even if you have a back end that is not branch cache capable. Now, one of the drawbacks here is that because each client will have a separate server secret that it's using to generate its own keys, that's okay because you don't have to know what the server secret was. But on the other hand, that means a different client that uploads a changed copy, you won't reuse any of the segments. Where this is useful is if you have one client that's generating all the changes or most of the changes, or if you want to be able to just avoid downloading a second copy from the cloud of something between changes.
What if, what breaks if you just have all the clients share the same server secret?
Nothing. You just have to secure that is one thing.
Right.
And specific to Windows, we don't have an API to set the server secret. It's a command line.
Yes, you do. Yeah, it's command line. Yeah, that's it. Yeah, it's a command line.
Yeah. Now, if you can
So somewhere
call,
there's an API that's not exposed.
yeah. Well, you can certainly call the command line and change it yourself. You may not want to do that if you envision that you might ever run on the content server side. But if from a protocol layer, there is nothing wrong with all the clients knowing what the server secret is. Just that you don't want to let that get to anyone who's not already authorized to access the data, so same security level.
In this model, what you're calling the client is just a local extension to the service, really. So it's not really a different. I mean, you have to think about the security, but you don't have to, I think you'd think of it as just a separate process.
Mm-hmm.
In summary, keep the server secret about as secure or more secure than, say, an SSH private key.
Yeah. So I know that I've gone a little bit over time, so I'm sorry. But we have a couple avenues where you can follow up with us. The branch cache alias, I'm happy to help out with. If you find issues in the protocol documents, we can get TDIs entered on that. And branchcache.com will redirect you to the TechNet page about branch cache. So, that's all the session objectives, and just for convenience, here is the list of protocols that we were talking about. We've had some good questions in between, but if there are any to close with, okay. Thank you all for your time.